When a current-carrying conductor is placed in a magnetic field, it experiences a force. This is termed the motor effect. This is the underlying principle by which a DC motor functions as it converts electrical energy into mechanical energy. As voltage is supplied, the circuit, or in the case of a DC motor, the coil of wire, acts as a current-carrying conductor, thereby producing a magnetic field surrounding the conductor. This magnetic field interacts with an external magnetic field, giving rise to a resultant force in a particular direction acting on the conductor relative to conventional current and orientation of the magnetic field. The force experienced by a current-carrying conductor in a magnetic field is given by the equation F equals BIL sine theta. To determine the direction of the force, the right-hand palm rule is applied. The DC motor also experiences these forces in opposite directions on each of its opposite two sides of its armature, which causes its rotation due to torque in a certain direction about an axis caused by its interaction with the magnetic field. In this case, right-hand palm rule is also applied. To construct this simple DC motor, we first got a piece of styrofoam which formed the armature. Then we got a wooden dowel sanded on both ends and punctured a hole into the center of the styrofoam to fit it through, forming the axle about which the armature rotated. Next, 0.26mm copper wire was repeatedly wound around each side of the armature in the same direction. For this DC motor, we have completed 40 turns on each side, constituting a total of 80 turns around the armature. This was done as torque is directly proportional to the number of turns around the armature, according to the formula torque equals to NIAB sine theta. The ends of the wire were sanded to minimize resistance and ensure optimal electrical conductivity. A multimeter was used to test their conductivity by carefully pressing down the lead needles onto each end of the copper wire. A split ring commutator was attached to the ends of the copper wire by cutting two thin pieces of aluminum foil and tightly wrapping them around each exposed end of the copper wire. To ensure that maximum torque and rotational speed was achieved, the commutator ends were positioned horizontally about the axle when the armature was vertical in its maximum torque position and the coil horizontal. Two pieces of larger aluminum foil were folded down to thin sheets attached to the wrapped wire ends with sticky tape on the top and bottom edges to firmly attach the commutator to the axle and maintain electrical contact with the armature coil. The split ring commutator ensures that the current reverses direction every half rotation, so that the force acting on the coils also reverses direction every half turn. This therefore causes the torque to remain unidirectional, allowing the armature to freely and continuously rotate in one single direction without stopping at a half turn, then reversing its direction of rotation. Four large angle brackets were set up as shown and affixed with duct tape onto the wooden base. The axle holding the armature was loosely inserted through two opposite face brackets to minimize friction and allow constant rotation. Then two small pieces of aluminum foil were smoothly folded and inserted between the alligator clips to form the brushes. Two strong neodymium cylindrical magnets were first tested for their polarity, then attached onto the front of the other two brackets to form the stator, which created a magnetic field through the motor. Finally, the alligator clips were attached to the terminals of a 9-volt alkaline battery and the brushes held against each side of the commutator to create a point of electrical contact for the current to flow and eventually interact with the magnetic field to generate a rotational force on the armature known as the motor effect. Magnetic flux constantly changes as the angle between the normal to the surface area of the armature coil and the magnetic field fluctuates with respect to its constant rotation. According to Faraday's law of electromagnetic induction, the magnitude of electromotive force produced is directly proportional to the rate of change of magnetic flux over time, as shown by the equation. Following Faraday's law, we know that there is an induced current flowing through the coil due to the supply EMF. This is clearly indicative of an energy conversion taking place where the initial electrical energy is converted to kinetic energy as a result of the armature's constant rotation. Therefore, in order to comply with the law of conservation of energy, the rotational speed must decelerate until it reaches a constant final speed. However, if this was not the case, the induced current would cause the rotational speed of the armature to keep increasing, as the torque is directly proportional to the magnitude of current, thus producing more net voltage and kinetic energy, consequently violating the law of conservation of energy. How do we account for this issue in a more logically based manner? This is where Lenz's law comes into play. The law states that the induced EMF or back EMF is produced in such a way as to generate a current which counteracts the change in magnetic flux which caused it. Therefore, Lenz's law accounts for the negative sign in Faraday's law of electromagnetic induction, indicating the opposite direction of induced current flow. It is an extended application of the law of conservation of energy in the sense that the back EMF induced by the change in magnetic flux reduces the net voltage according to the equation. Net EMF equals the voltage of supply minus back EMF. This reduction in net voltage indicates that the net current is also decreased according to Ohm's law, V equals to IR. Since back EMF is directly proportional to the rate of change of flux, we can deduce that angular velocity, which is dependent on the angle of change, is also proportional, hence increasing the rotational speed of the armature, resulting in a subsequent decrease in electrical energy and increase in output kinetic energy, thus following the law of conservation of energy. In a DC motor, the back EMF produced is directly proportional to the speed of rotation of the armature. This means that in its initial stationary position, the back EMF is zero, as there is zero magnetic flux and therefore the net voltage and subsequently the net current is at a maximum. As it begins to rotate, a back EMF is produced due to change in magnetic flux, and the net voltage and current begins to drop. Considering the direct proportionality between current and torque, we can infer that the torque will also decrease, therefore slowing down the armature's rotational acceleration. When the back EMF produced is equivalent to the supply voltage, there is net zero voltage and therefore net zero current flowing through the coil. Subsequently, the armature reaches a constant max speed with no net acceleration, thus demonstrating the motor effect. This can be extrapolated when considering its power consumption given by P equals to IV. As mentioned previously, as back EMF increases, the net voltage and current decrease, thus increasing the speed of rotation. Therefore, we can conclusively say that a larger production of back EMF increases the efficiency of the motor as it significantly reduces its power consumption, while still running at a max constant speed.
I'll be popping bottles, sparkles and champagne.